Hi, welcome to Unit 24. In this unit, we're going to basically use something called spectroscopy to identify elements or atoms. So it's every atom has a unique signature when it comes to light emitted from it. This science or this branch of science was started actually by astronomy and then later on now is used in all kinds of fields, including chemistry, physics, basically the study of trying, I don't know what it's called exactly, it's criminology, I guess, where they study how basically a compositions of elements and how they go inside and so on and so forth determine uh, 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 substances existing or not existing in a certain place. Anyway, so basically every element has a unique signature, as I said, okay? And it started really by the study before that. For example, in the case of hydrogen, it has unique signature. There are four lines that are emitted by the hydrogen atoms. Okay, so if you have hydrogen gas, you isolate it, you excite it, you put it in tremendous voltage, for example, or heat, then it's going to glow. As it glows, you run it through a apparatus that I'm going to describe right now, that basically you run it through something called diffraction grating, or even a prism is going to break into four lines, okay? And it's always like that. So if I see these four lines, I know there is hydrogen in there. That's basically in a nutshell what this is, okay? Other elements have their own signature. They have probably more than that, and they probably have different values for this lines, okay? And the funny part of it, or at least the beautiful part of it, if you wish, that these lines, they are not just in the visible, they extend to the ultraviolet region and they're beyond basically the violet for shorter wavelengths. And they extend actually for longer wavelengths into the infrared and beyond. So you can have far more information about the composition if you can somehow break the light into different components in both sides too, not just in the visible. So again, discuss how spectra differ according to composition, temperature, and density, list Kirchhoff's laws, and describe the condition that produce each type of spectrum. And basically, you have either absorption spectrum, where you have, for example, light coming from a hot source, going through a gas, and then going through to the measurement or to our eyes or to whatever we're measuring it. If we do an analysis, we will see the entire spectrum as it's emitted, the entire basically continuous spectrum, except it's missing some lines. So in this case, we say these lines have been absorbed by the intervening gas. So this is our absorption spectrum versus an emission spectrum where, for example, you have a gas that is glowing coming out, that is hot and is emitting radiation. So it's glowing. And then when we analyze it, we will see that there are lines existing versus a background that has nothing. So in this case, it's an emission spectrum because it's light that is emitted by the source, okay? And then describe the different properties that may alter the strength of the spectral lines, okay? So, again, we have a light source in here. We run it through for something called a diffraction grating, okay? Something called a slit, which is really a small, tiny opening, okay? That's because when you have a small, tiny opening that is of a extremely small size, small width, I should say, then light as it goes through, because it's a wave and it has a wavelength, starts to go through the edges and starts to go both ends. So the spectrum widens. And then it splits into the kind of different components in there, okay? So you have the red going one way and so on and so forth. To exaggerate that, so we have a narrow band now. We run it through either a prism or a diffraction grating. In spectroscopy, usually we use the diffraction grating. So what is a diffraction grating? I used to have one, but I'm sorry, I have it in here. Here is one that we use in our laboratory, okay? So what it's made up of, if you can see in here, this one is made up of 1,000 lines, okay? So 1,000 lines, it means that there are 1,000 lines in here divided per millimeter. Per millimeter. So this is not a millimeter. This is probably about 2 or 3 centimeters. It's about an inch. It's actually slightly more than an inch, so almost 2 inches. So it's about 5 centimeters. So this is 50 millimeters. Each millimeter has 1,000 lines. So that means there are 1,000 openings. So the light as it goes through, okay, is going to have it's going to be broken down into its component, just like the rainbow, okay? Because the light, I mean, basically the blue or the violet diffracts less than or makes an angle less than the red. So the red will find itself way bent versus, for example, the violet. And anywhere in between is going to be somewhere in between, okay? So it depends on the wavelength. So that's basically the idea. So you have collecting device that collects light from the star, goes through a slit, an opening. That light now is basically going in the same direction, goes through usually, like I said, a diffraction grating. If you want to, you could do a prism. And then at the end, it's going to be broken. Then you take those and you measure their how much they diffracted, and you know exactly what the wavelength is based on the angle, that is made between this axis, this line, where it came from, and how much they bent. Okay, so that's actually a lab for our astronomy lab. We do that in the lab actually. Mr. Bohr came up with a model for because first of all, this was studied before, okay? Mr. Balmer, actually, part of his graduate work was to measure those lines for hydrogen, and he found the 4 lines, as I said, and he found an empirical law that this wavelengths, basically, they depend on the number. There is an integer difference between them, okay? Mr. Bohr came up with a model, basically, for the hydrogen atom, liking it to a solar system where the nucleus is in the center, and the electrons orbit the nucleus, just like the planets orbit the sun. There is a problem with this model if you do it really for electrons and protons, because electron will become highly unstable. It will not stay there. It's going to radiate energy and fall into the nucleus in a matter of no time. So in order to fix that, he used something that we talked about in a previous unit called Planck's law. He used Planck's law to argue that the reason why the electron stays in orbit is because of something called standing waves. And what a standing wave is, if you have a guitar and you play it and you play a specific tone, the wave is on the string of the guitar will form kind of a note, okay, with 2 points that are fixed called antinodes, or they form two notes, and one antinode, or 2 antinodes. Antinodes are just the openings, the thickness thing, and the nodes is when the string is actually stationary. So it's going to form this pattern that stays there. So he's saying in here is that the electron, the reason why it doesn't fall onto the nucleus is because it's in a standing mode, basically standing there, just like you have waves on a string. And he argued that, and he used that to his advantage, and he found the exact spectrum that Mr. Balmer has found in a experimentally, basically measuring with those integers. And the interesting thing is that he argued that the position of the electron is just square of an integer. So n is a number that's either 1 or 2 or 3 or 4 or 5. So they are integers, not like 1.2, for example, not decimal points. Okay. So when you square 1, it's going to be 1. So the first electron is at this far from the nucleus, 0.053 nanometers. A nanometer, just to remind you, it's actually 10 to the negative 9 meters. I'm sorry, it's not 10 to the negative 3. So it's 10 to the negative 9 meters, okay? So it's a billionth of a meter. So this is 500th of a billionth. So it's extremely small size, okay? That's from unit 3 if you want to go back to those conversions. So that's basically one thing, okay? And if it is on an excited state from n equal to 1 to n equals to 2, it's actually 4 times this number, which puts it around 0.2 nanometers, okay? It's still tiny. And then if it's even more than that, it's going to be 9 times this number, which is probably just around 1.8 or something like that. or just around 2 actually. No, it's about 1.8 nanometers. So it's still very tiny. Okay? So all of this are very tiny, even when it's a third level. Okay. Okay. Then he also found a match for the energy levels that correspond to the same numbers that and this is actually the Balmer correspondence. This is new, by the way. Mr. Bohr came up with that number new. But the energy levels, this is exactly like Mr. Balmer has predicted. It's an energy divided by n squared. Not only that predicted the behavior, dependent on integer squared, but he also found the match for the values for the energy. Negative 2.18 times 10 to the negative 18 joules per divided by n squared. Now, the negative sign has a meaning in that the electron is actually bound to the nucleus. That's what the negative sign means in here. So if I want to free that electron, move it freely, I have to add the same amount of energy so that it will have zero energy. Basically, it's free. Okay? So that's what the negative sign means. Usually, if you took chemistry or you saw this number in chemistry, and even in physics, they don't like to use these tiny numbers. Okay, who remembers 10 to the negative 18? So it's better to use whole numbers. So you divide it by the charge of the electron, and you use something called the electron volt, and the number is actually around negative 13.6. That's still a tiny number. So whether you express it in terms of the energy in terms of electron volts, or you express it in terms of joules. So in either case, the energy is tiny. That's basically what it is. But remember, we're talking about tiny particles. The electron has basically no mass. I mean, it's 10 to the negative 31 kilogram. It's a very tiny mass. So although for us it seems like it's a tiny energy, and it is, but for an electron it's tremendous energy. In order to move an electron from this level to the next level or to free it up, you really need a lot of energy when you are an electron. Okay? So that's basically what it is. That's why it's tightly bound to its hydrogen atom. You really need to heat the hydrogen a lot in order to free it from its electron, or to free its electron and basically you have just a nucleus by itself. Okay? That's exactly what's going on inside the sun, because it's super hot that basically it's in that state. Okay? Remember, in another unit, we said the core temperature of the sun is 15 million Kelvin, and that's a lot of temperature. So that's a lot of energy. So it's going to free all of the electrons from all of the hydrogens. Okay, so this is a representation of the atom now. So this is not how the atom looks like, but just a represent to give you an idea of how it looks like, okay, based on this model anyway. So from n equals to 1, that's the ground state. That's where the hydrogen would want, the electron would want to be in the hydrogen atom. N equals to 2, n equals to 3, n equals to 4, and so on and so forth, okay? The gap in terms of the radius starts to grow like the square of these numbers. The energy level starts to shrink like 1 over the square of these numbers, okay? If an electron was sitting in this range and falls just to the lower level immediately next to it, it's going to emit a very long wavelength. Why is it a very long wavelength? Because the gap energy is very small. So the frequency is very low. And remember from a previous unit, if the frequency is low, the wavelength is very long. So the light will appear red. If it makes a big jump in terms of energy from this level all the way to here, then in this case, the energy is high, the wavelength is short, and the light will appear bluish color. Okay. As a matter of fact, the wavelength is here 486, whereas in here is 656 nanometers. So that's basically how the spectrum is. As a matter of fact, since I'm talking about it, E and lambda are connected through one another through this expression, which is h times the frequency, and the frequency is c over lambda. Remember, frequency times lambda, according to the dispersion law, is equal to the speed of light. So h is a constant, c is a constant, and lambda is the wavelength. Smaller energy, because the gap is small in this case, longer wavelength, and vice versa. Bigger energy, because there is a bigger gap in here, then the wavelength is small. Okay, and that's basically how this works. For hydrogen, it has a signature of 656 nanometers. That's red. And it has also a signature at 486. That's also a blue color. But that's not the only colors that we see invisible. There are 2 more, okay? I mean, the others are kind of faint, but they are there, okay? So these are the so-called Balmer lines because they're in the visible range. And as I said before, there is from 3 to 2, from the level 3 down to level 2, just a small gap, the color is red. From 4 down to 2, it's actually blue. From 5 down to 2, okay, it's actually violet of some sort, okay, or indigo. And then from 6 to 2, it's even shorter wavelength. Oh, there is a big gap between 6 and 2 versus, for example, between 3 and 2, okay? So in this case, the energy is super high, the wavelength is super low. As a matter of fact, this is the last one we will see. If you go from 7 to 2, it's going to be in the infrared. And all of them, they involve the lower level 2. These are the ones we see. We don't see the ones that go all the way down to 1. Because their energies are actually, their energies are in this side. I made a mistake earlier. So from 7 to 2 will be on this side, okay? Because they're even, I'm sorry, what am I saying? From 7 to 2 is actually going to be on this side too, okay? Because 7 to 2 is a big gap. 8 to 2 is a big gap, okay? But the difference between 7 and 8 is very small. So if something from 7 to 2 or 8 to 2, it's going to be very, very close from each other. But the point being in here, 1. Nothing in here says coming down to 1, because coming down to 1, it involves even more energy. So it's going to be even on this side more. We don't see those. Coming down to level 3, for example, from 5 to 3 or 4 to 3 or 6 to 3 or 7 to 3, that's going to be on this side. We don't see it. So those are different lines that are going to be in the infrared, involving higher levels, basically coming down to level 3, or coming down to level 4, or coming down to level 5. They're all going to be on this side. Coming down to level 1, they're all going to be this side, okay? Even coming down to level 2, maybe on this side, if we come from 6 or 7 or something, there will be going to be, so we don't see them. So these are the visible spectrum. So those are the four lines of hydrogen. So if you have a hydrogen sitting in a tube, for example, and you put it in tremendous voltage, you're going to produce in the visible range, the one that you and I see, these 4 colors. And we see that actually in the lab here on campus. Okay. Different atoms will have more energy gaps in here, will have more electrons to jump. So there will be more lines. That's in a nutshell. More players, namely more electrons, more hops basically in between. So you definitely will have more lines, and this is how helium is different compared to hydrogen. But helium's red line is not the same red line. So they're almost aligned, but they are not. So if I see a value in here, I know it's different than this value because this one is signature of helium. By the way, in a specific lab, for example, you may have, under some circumstances, some lines that don't appear. They're too dim to be seen, okay? So in this case, you will only have a few lines, and those are enough to identify the element. One line sometimes is enough to identify the element. The second line is just to confirm it, okay? So that's basically in a nutshell. So every element has a signature, depending on its structure. Okay? Because its structure is the one that dictates that. The absorption line, I mentioned it briefly, is that, okay, if the source sends a spectrum in all visible, in all ranges basically of frequencies, and there is something in between, like a cloud of cool hydrogen, for example, then hydrogen will absorb just the ones for hydrogen. The others, they don't care because it's only hydrogen in there. So in this case, if I run a spectrum, it's going to look like this. It's going to have some missing lines. Where does these lines happen? They were absorbed by the hydrogen existing in this gas. Whereas if I take the spectrum coming from that star, I will have a continuous spectrum. I will have the entire spectrum. Nothing is missing because I don't have an intervening object in here like this cloud that exists. Okay, so that's just distinction between a continuous spectrum and an absorption spectrum. And here, this is actually an emission spectrum because this gas in here inside this tube has been excited to the point that it started to glow, And then that glowing is showing in this one, whether it's helium or hydrogen, okay? So the distinction in here, these are the different spectra. A continuous spectrum is where there is all of the lines are in there, basically. An absorption spectrum, an emission spectrum is this one. Basically, all the light are missing except some, okay? Because the gas was too cool, and then now all of a sudden it's received the radiation, so it gets excited. This is the opposite. The gas is actually too hot compared to its environment, so it starts to emit radiation, okay? Starts to emit radiation, and that brings me back to the black body radiation from previous unit. The black body radiation, if it's hotter than its environment, it's glow. If it's cooler, it's going to absorb. And if I look at the spectrum, for example, analysis in this case coming from a star like the sun, for example, I would see everything except some missing lines because of the atmosphere of the star. The atmosphere of the sun in this case has these elements in it, signature of hydrogen absorbing those spectra, sodium, magnesium, another line of hydrogen that confirms definitely that it was hydrogen all along, and some lines of calcium that give me the composition. So we run this one for the sun, and we find that 70.6% of the sun is actually hydrogen. 27.4, so if I add these two numbers, I'm already at 98%. So the 2% in here that remains is just these traces of the other elements. The biggest one is actually oxygen and then carbon. So those are dominant, but they're dominant in the 2% that remains to be split between them. Actually, the 2%, one of them is oxygen. One of those percentages is oxygen. So the other 1% basically is split between carbon and everybody else. But carbon takes 1/3 of what remains, okay? And 2/10 what remains is actually iron. And the other 1/10 is actually nitrogen. So you're looking at all of the elements in here that dominate in the atmosphere of the sun. They're actually by far hydrogen and then helium. And then the traces of the other element dominated by carbon and oxygen, and the rest of the other elements in the periodic table, including uranium, for example, which is a 10 to the negative 2. It's a billionth of everything as percent. Okay, so this is a percentage, okay? And gold is, what is it, 10 billionth, okay? So it's still tiny. So we can't really go and collect gold from the surface of the sun. So hopefully this is informative. It's about the spectra of how we identify elements using just basically a spectroscopy, which is a combination of a slit, an opening to basically collimate the beam, and then through a diffraction grating or a prism, and then measure the wavelength based on how much bending there is. Once we have wavelength, we know exactly what's present in there because we know each element has a signature. That's how we know what we know about, for example, the stars in general, that this star is this much and this star is this much, especially when it comes to stellar compositions, these two numbers. Because if I know there is far more hydrogen, for example, than this, then this star is probably an older generation star that formed immediately after the universe formed. Then newer generations, they will have less and less hydrogen in it. And depending on how much hydrogen also tells me about the age of the star, because the hydrogen is the one that exists mainly in the stars, with helium, because helium is the next element at the ratio of 3/4 basically hydrogen and 1/4 helium, and everything else is just a negligible amount. Thank you.